Hello everybody. We now begin our second lecture on the introduction to recursive formulations for algorithm design. We had discussed in our first lecture the difference between algorithms and programs and our need of pseudocode, and we said that algorithms consists of defining initial solutions, their analysis, solution refinement, and the development of data structures. We also saw how we shall use recursive definitions for initial solutions and use induction and recurrence equations for proof and analysis. We saw two examples where we did solution refinement and analysis through the understanding of the recursion structure, and then we shall see again in more details about how to develop this through certain case studies before we go to the general methodology. We saw two examples, finding the largest and finding the largest and the smallest, and in both the cases we first developed a sequential recursion. Then we developed a generalized recursion, generalized recursive formulation, using the split paradigm, splitting a list, and then we examined the possibilities of what is the best possible optimal choice of split. And we found that while solving the largest, all the choices were equal, whereas for finding the largest and the second largest, we found that all the choices were not equal, and certain choices were better than other choices. Today, we shall start with the third problem in this category, is to find the largest and second largest. So, our problem is to find the largest and the second largest of a set of integers. Well, let us assume that they are all positive integers. As usual, we shall follow the same principles that we had done in our first two examples. We will develop a basic recursion algorithm based on a trivial algorithm that we would have done, in which we would have initialized max1 and max2, where we would initialize max1 to the first integer x1 and keep max2 as a null value which is less than the smallest number possible, and then compare it with every other number, and while comparing with every other number we would then update both max1 and max2 in a sequential fashion, and by this we would require two comparisons at every step, and we would solve that problem in 2 into n minus 1 comparisons, that is 2n minus 2. So let us write that down as we had written in the previous cases as well. So our recursion will be max1, max2 L. Let L equal to x1, x2 up to xn. If size of L is equal to 1, then we return x1 and null, and we assume null is the smaller than the smallest of all the numbers, so that when we have a second number it gets updated. Then we create L dashed as before is equal to L minus x1, and we recursively call max1 max2 on L dashed to get y1 and y2. We are following the same principles, almost the same principles that we had done to do max and min, only the comparison will be a little different after it returns from the recursion. So now when it returns from the recursion, all we have to do is compare x1 with y1, y2 and come up with the result. So what we have is, if x1 is greater than equal to y1, then we have m1 equal to x1 and m2 equal to y1. Else we have m1 equal to y1, but now x1 has to be compared with y2 to determine what is m2. And if x1 is greater than equal to y2, then we have m2 equal to x1, else m2 equal to y2. This is the else part, and this ends my else part of the program, and now we return m1, m2, this is what we return. So this is almost identical to the way in which we solved the max-min problem, only the comparison that we do after we return from the recursion is slightly different. So let us go back to our example that we solved. Our example was 5, 8, 3, 1, 2, 6, 12. So again 5, and this leads to 8, 3, 1, 2, 6, 12. This 8 is taken out, and we have 3, 1, this is all L dashed, 12. Then 3 is taken out, we have 1, 2, sorry, there was a 6 here, 6, 12. Then 1 is taken out, and we have 2, 6, 12. Then 2 is taken out, and we have 6, 12. Then 6 is taken out, and we have 12. And 12 is a base condition, and 12 being the base condition, we start returning from the recursion. So this gives a value of 12 null. This, when compared with 6, here this will now return. So this returns 12 null. This, when compared with 6, will return 12 6. This, when compared with 2, will return 12 2. As per the comparisons done at this step, this, when compared with 1, will return 12 1, and then again when compared with 3 will return 12 1, when compared with 8 will return 12 1, and finally when compared with 5 will return 12 1. So this is how it works, and based on this working we can again see that the recurrence here, that the recurrence equation that is formed, is Tn is equal to Tn minus 1 plus, there are two comparisons, this is 2. There are two comparisons. This is for n greater than 1, and it is 0 for n equal to 1. So this is identical because here there is one comparison which is taking place here, and in the else part, in the worst case, there will be another comparison. So this is identical to our max and min problem, and here we will get our complexity Tn is equal to 2 n minus 1, which is the same as 2n minus 2. And once we have got this, again the proof by induction is also straightforward and doable. Now we come to the generalized recursive formulation, and our generalized recursive formulation will again follow our principles that we have done for both the largest and second largest. So we now write down the more general formulation where we split the L list into two parts, and we will decide on how to split. So we write max 1, max 2, B. This is our second algorithm, or second initial definition. So then again let L equal to x1, x2 to xn. If L equal to 1, return x1 null. Now again, like in the max-min case, our other base condition is when there are two elements, because we can solve that by a single comparison. There we do if x1 is greater than or equal to x2, then we have m1 equal to x1 and m2 equal to x2. Else we have m1 equal to x2 and m2 equal to x1. This is what we have at this stage if L is 2, and we return. So if that is the case, this is what we do, and we return accordingly. So here we put this whole thing in a bracket. If this is the case, then we put all this and we return m1, m2. If this is not the case, that means it is the general recursive condition. That means it is the else part. So that means if L is greater than 2, then we start our processes. So the first thing that we do is we split L into two non-empty sets L1, L2, and we get the response back. So we get y1, y2 equal to max 1, max 2b, L1. We get z1, z2 equal to max 1, max 2b, b, L2. Now once we have got this, which is identical to our max-min problem, we now start the comparison of y1, y2 with z1, z2 to really determine what would be returned by this function. And in order to do that, what we do is we now compare if y1 is greater than or equal to z1, then we have m1 equal to y1, and if m1 is y1, then we now compare z1 with y2. If z1 is greater than or equal to y2, then we have m2 equal to z1, else m2 is equal to y2. This is one part. The other part is if y1 is less than z1, that means else. When we have that else part, then we know that m1 is z1. So now m1 is z1. So now we have to compare y1 with z2, and so we have if y1 is greater than z2, then we have m2. So we need to have m2 equal to y1, else m2 equal to z2. This way we have now got our m1, m2, and we return m1, m2. This is almost identical to the way in which we solved our earlier problem of max and min, only the comparison after returning is different. And it is not difficult to see that this will again get optimized by the same mechanism by which we got the optimization of the max and min. That means the optimal splits, the recursive equation, the recursion will be Tn will be equal to Tk plus Tn minus k plus 2 if n is greater than 2. As you can see, even though this whole sequence of post comparison is a long one, there is only two comparisons. Either you do this and this, or you do this and this. So there are these three comparisons, of which only two of them will actually happen, which is equal to 1 if n is equal to 2 and equal to 0 if n is equal to 1. And as we have seen in the previous case, we will get an optimal value for if we split, if we choose, except for the any other case, the optimal split will occur for k equal to 2. And if we choose k equal to 2, then this whole equation will now give the is as what we will finally get is 3n by 2 minus 2. Ceiling of that means the immediate integer after this if it is a fraction. So this is the complexity that we will get, which is a better and an improved version of the complexity that we will get from our previous case where we did a sequential split where we got 2n minus 2. So this follows an identical clockwork fashion as we have seen in our other previous example. Now let us see whether there is something more to this if we build our tournament structure. So let us build our tournament structure and let us see what happens if we build a tournament structure with this case example. And though we can build it in many ways, we now build the tournament structure in a particular way. We are building it by choosing pairwise and selecting what we do. Again we choose pairwise and again we choose pairwise. And if we do this, then our comparisons that come up at every point in time, this will return 12 null, this will return 6 2, this will return 12 2, this will return 3 1, here we will get 8 5, this will return 8, 1, and this will return 12, 1. And as we can see that by this, the number of comparisons that we have at every stage, at this point we have got 1 comparison, 1 comparison, 1 comparison, 0 for 12, 2 here, 2 here, and 2 here. So we get a total of 9 comparisons. We get a total of 9 comparisons, which is compatible to our 3n by 2 minus 2 ceiling formula. And we know that our split that we had chosen, our generalized split rule, general split rule, as in the Max-Min problem, our general split rule will be that if n equal to even, split even, even. If n equal to odd, split odd even. And this generalized split rule will again yield the same formula of 3n by 2 minus 2 in the worst case. Now let us look at this tournament structure a little more carefully. So we redraw the tournament structure. And now in this tournament we first find only the largest. We build up this tournament structure and find only the largest. So in the first step we find only the largest. So the largest here is 8, 3, 6, 12, 12, 8, 12. And we know that max 1 is equal to 12. This we now know. Now we apply a very interesting rule. The rule is as follows. The observation this is a very important observation. Max 2 must have been compared with max 1 in the tournament. This is a very interesting observation. It says that the second largest element must have been compared with the largest element at some point in time. So if the second largest element has been compared with the largest element in some point in time, to find the second largest element, all we need to do, so this is now the rule. Now the interesting part is, to find the second largest element, to find max 2, we need to only compare those elements which were compared with max 1. This is a critical observation, which means who were compared with max 1? Max 1 is 12. So 8 was compared with max 1, 6 was compared with max 1. And nobody else was compared with max 1. And if we see those who were compared with max 1, the largest of the two will be max 2. So, we now don't need to compare various other elements. All we need to do is the algorithm now based on this observation. So, this observation leads to this idea, and this observation leads to follow the path back of max 1 in the tournament. So, we follow the path of max 1 in the tournament, and along this path we retrace this path back, and as we retrace this path we find all the elements with whom it was compared, and the largest of those will become max 2, and you will get max 2 equal to 8. And since you are getting max 2 equal to 8, you can observe that what becomes the complexity now? The complexity is that we now had, we had n minus 1 comparisons for max 1. But for max 2, we now have the length of path of tournament. So, this tournament has got a height. So, this height of the tournament is to be minimized. So, if we do a sequential comparison one after another, we will see, as we saw in this example, this sequential comparison one after another gave our height to be n minus 1, because at every step we are going down by one step, so we get height of n minus 1. If we do a split of 2n minus 2, then at every step we reduce by 2, so our height, since we reduce by 2, if we started with 10 elements, in the next step we will have 8, in the next step we will have 6, 5, 4, so the height of that tree will become n by 2. Since the height of that tree now becomes n by 2, therefore, in the worst case, the comparison would require at least n by 2 to find max 2, which means that max 1 will require n minus 1, max 2 will require n by 2 minus 1, which would again give us 3n by 2 minus 2. But can we make the height of the tree minimized? You see this case. If we compare them all pairwise and build it up pairwise, then we will see that the height of the tree can become minimized. And this gives an idea that we can build the tournament in a much more intelligent fashion. And we shall discuss this in the next slide. So, we redraw our example tournament, and we see that in order to minimize the height of the tree, we will create the tournament structure in a balanced fashion. So, we will create a balanced tournament. We will create a balanced tournament. What do we mean by a balanced tournament? The balanced tournament is one where the height of the tournament is minimized. As we shall see here, that we are creating the tournament in such a way that at every stage two elements are compared. If they are all even, then one is left out. And then in the next stage, all those who have won there are again compared. All those who have won there are again compared. And in a balanced tournament, the height will be log n to the base 2 ceiling. That means for 7 elements, the height can at most be 3. For 9 elements, the height can at most be 4, and so on and so forth. So once we have a balanced tournament, then we know that to find max 1, for a balanced tournament, to find max 1 will require n minus 1 steps, and max 2 will require log n minus 1 steps. So total number of steps will be n plus log n minus 2, which is a big reduction again from 3n by 2 minus 2, which is n plus n by 2 minus 2, because log n, as it grows, when n is large, log n is much smaller than n by 2. So we will create what is known as a balanced tournament to minimize the height of the comparison. Now we see what is the fallout of this. Not only have we got an optimal algorithm by doing what? Here the split was decided because the algorithm wanted to remember the tournament structure. As we saw in this case, it remembered what it had done in this tournament, and based on the past comparisons, it came back and used the tournament structure. So we will now store this tournament structure, and we will use this tournament structure to build a much better algorithm. So the storing of this tournament structure, so we now have what is called a data structure that we will store, and this data structure is this tournament comparison tree. And we will use this tournament comparison tree to solve our problem. Now let us see what is the fallout of this tournament comparison tree, and can we extend this further to get max 3? Can we extend this further to get max 4? Can we extend this further to get max 5, etc., etc., etc.? But before we come to that tournament comparison structure, I wish to revisit the max and min. Let us look at what our comparison does. We have already seen this is what our comparison does. Our basic max comparison does this. And if we revisit max and min, we will make another observation that during this comparison, in the first level of this comparison, where there are elements which are 8, 3, 6 and 12, and we will determine that if there are even elements for the time being, then after pairwise comparison, after we do pairwise comparison, we create two sets, win and loss. Those who have won in the comparison and those who have lost. And if there is a single element remaining, we put it in both the sets. and the winner will come from the win set. That means the max will come from the win set and the min will come from the lose set. So this yields us approximately n by 2 minus 1 comparisons for finding the two sets, because we are doing pairwise comparison, and then from each of the two sets n by 2 minus 1, again we will get n by 2 comparisons minus 1 comparison, we will do n by 2 comparisons to get the first set, approximately n by 2 comparisons to find the first set, n by 2 minus 1 to find the largest from the winner set, and n by 2 minus 1 to find the smallest from the loser set, which again gives us our 3n by 2 minus 2 formula. So even this tournament structure not only enables us just to get the largest easily in n minus 1 steps, but it enables us to give an idea of how to find the largest and the smallest again in 3n by 2 steps. So this comparison tree or this data structure is an extremely important element for our algorithm design process. Now let us see how this data structure can be used for doing something further. So let us redraw it again. So we redraw this comparison structure, and typically we try to redraw this balanced comparison structure, because we have seen that this balanced comparison structure has enabled us to find the largest element in its optimal number of steps and the second largest element again in the optimal number of steps. So we know how to find the largest. Now let us see how we proceed to do better and better. So what we have done is we have found the max 1 equal to 12. We can also find the minimum now, and let us say we have found the minimum, and we have found the minimum equal to 1. Now just follow me about what I am doing. We create a value called null which is smaller than the smallest. And what we do is we remove the max. So we remove the max element and put it in a list L. So L has got the max element, SL is the sorted list. SL has got the max element. We remove this max element and we replace this max element by null. So we remove the max element, we move along the path, we remove this max element. How to identify the max element? We can go along this path from the max element and we remove this max element and replace it by, we move back along the path of the max element and we replace it by null. And we replace it by null. We don't do it here, we just do it here. So we have removed the max element, put it into our list SL, and we have gone back along this path. We have gone back along this path and replaced it by null. Then we again retrace the comparison only along this path. If we retrace the comparison only along this path, then what do we get? The new values here will become 6 because null is smaller than the smallest, and 6 and 8 will compare to give us 8. So once we have 8, we know that we have got max 2 equal to 8. So what do? We remove this element, and we remove this max 2 element. We remove this element, put 8 here, follow this path back to its trace and make it null. So we have gone along this path to make it null. And then again we retrace this path back from bottom to top, and as you can see that the new comparison will be 5 here, 5 here, and 5 and 6 will compare to give 6. And lo behold, we have got max 3. And how many steps we required? We required again log n plus log n, one step down and one step up. So approximately log n steps were required to get the second max, the third max. And we go on following this. Now we remove this element, and along this path we make this null. And once we have made this null, the comparison again starts from the 6th base below. This becomes 2, this becomes 2, and now this becomes 5. And once we have 5, if we just follow, we remove 5, 5 becomes our next element. And we trace the path along 5 and replace 5 by null. And if we replace 5 by null, we get null here, we get null here now. And after we get null here, we get 3 here. And with 3 and 2, we get 3. And so the next element in the list is 3. And once we have got 3, we again delete 3, take this, make it null, and this now, as it comparison goes up, this becomes 1, and 1 and 2 get compared, and 2 and 2 becomes my next element. And once 2 becomes my next element, I remove 2, put it in a cell, and again follow the path of 2, remove it, make it null. And then in the next iteration 1 will come. So in the next iteration 2 is removed, made null, 1, 1, so this becomes 1. And finally we remove 1, and we have this set, and if we try to make 1 null now and start the process, then null will come out, and once null comes out, we know we have completed. So we have been able to do sorting, and how much we required? We required our complexity here for sorting. The total complexity which we had was n minus 1 for development of this tournament data structure, because we required n minus 1 comparisons, and we have seen that this tournament data structure, whether it's balanced or unbalanced, will require n minus 1, and we created this balanced data structure, and at every step we required log n comparisons to find the next value. So we required log n comparisons to find the next value, and now we will just multiply that by n so that we are able to we will now have multiplied that by n, and this will give us a famous approximately n log n algorithm, an order n log n algorithm, as we shall study this order in the next class, we will get what is an approximately n log n algorithm, or n minus 1 plus n log n algorithm for sorting, which is one of the top best sorting algorithms. This therefore highlights that our recursive definition process, as we go through that process, the recursive definition process enables us to decide on the splits, decide on data structures, and find the optimal algorithms. So let us review the three problems that we had. The three problems that we had were max, max min, max 1, max 2. These were the three problems. Based on these problems, we found out that we did this recursive definition. And from this recursive definition, for the max problem, any split is fine. Therefore, we did 1 n minus 1. So we choose 1 n minus 1. That means this is the split we choose, because this yields a very straightforward algorithm. For max min, we found a 2 n minus 2 split. And this gives us the optimal 3n by 2 minus 2. And for max 1, max 2, again we found that the 2n minus 2 split is also excellent. It is identical, and therefore the complexities that we got in each case, here we got n minus 1, here we got 3 by 2 n minus 2, here we got 3 by 2 n minus 2. Then, after we got this, the next step that we came to was refinement of the recursion structure. What we saw in these two cases is that while 2n minus 2 split is optimal, there are many others. So what we found out was that for max, no further refinement. For max and min, we found that this tournament structure, we can use this tournament structure. The tournament structure is in fact the recursion structure. The tournament structure for all the splits of optimal manner yields the same complexity of 3 by 2n minus 2. And we also found a new way of doing it by a data structure, by which what we do is, so we also found a new idea or of an algorithm where we say pairwise compare and form two lists of winners and losers, and then from the winners find the max and from the losers find the min, but it still does not change the complexity. Whereas from max 1, max 2, we found that among the many ones which give the odd even, even, even split, the balanced tournament split, which minimizes the height of the tournament, allows a more efficient algorithm. And since it allows a more efficient algorithm, it gives us n minus 1 plus log n. It gives us an n minus 1 plus log n algorithm for max 1, max 2. But here we have to store this tournament structure. And it also enables us to do sorting of a set of elements by using this data structure and repeatedly developing. So for the same problem, the same process, we have now got three mechanisms. The max algorithm can be defined to the max-min algorithm, which can be defined to the max 1, max 2 algorithm, which yields this new data structure called tournament. So this is how we go through our process. The final step is to write the program. So how do we write these programs? So we have our data structures, we have our algorithms. So for our max program, there is nothing to do. What we have to do is use a temporary variable for a 1 n minus 1 split max. And we will see that in one for loop in n minus 1 comparisons, the only thing we have to remember, our only data structure to remember is that single temporary current max. And that solves our problem, and we can write a single loop to solve it, which effectively means that the original algorithm that we had thought is obviously the algorithm of our choice. The only thing we have to think is there a better algorithm possible? That means, can anybody ever develop a better algorithm? And you can prove, and I leave this to you for you to prove, that finding the largest by comparison using only a comparison operation cannot be done in less than n minus 1 comparisons. For n numbers. If you do something other than comparison, some unique arithmetic operator and all, I am not saying that. What I am saying is, if you want to do it only by comparisons, then it cannot be done, because you can show that if you took less than that comparison, then there is one element which you did not compare. When we come to our max and min, we find that 2n minus 2 is equivalent to any of the other algorithms, whether it's using the tournament data structure or a balanced tree or anything else. Therefore, if we do a 2n minus 2, so if the final algorithm says that we will do a 2n minus 2 split, because that gives us 3n by 2 minus 2, and if that is the case, then our data structure is only two temporary variables, max and min. If there is one element, there is nothing to return, it is the same. Otherwise, if there are two elements or more, then you choose the first two elements, compare them and initialize them to max and min, and then you choose two elements at a time in a for loop. And if you choose two elements at a time in a for loop, you will be able to solve the rest of it in n by 2 iterations of that loop, n minus 1 by 2 iterations of that loop. And if you do that in n minus 1 by 2 iterations of the loop, you can easily show that in every iteration you are going to do two comparisons. So you will require 3n by 2 minus 2 steps. So a simple for loop will be able to solve this problem. Whereas for max 1, max 2, here we will have to really implement the tournament data structure, and there are many ways to implement the tournament data structure. One way is to maintain, a simple way is to maintain for n elements, if this is n, for n elements, to maintain a 2n size array, and for every pairwise comparison, if you compare element 1 and 2, you store it in n plus 1. So the comparison of 1 and 2 is stored in n plus 1. The comparison of 3 and 4 is stored in n plus 2, etc. And then you will require only n by 2 elements to store these, and then again the comparison of this part of the array, the comparison of this part of the array will be stored in n by 4 elements here. The comparison of this will be stored in some here, and so on and so forth. So you can easily do this. I am not doing this for you. There are some NPTEL lectures on programming and data structures taken by me long time ago. You will not recognize my size, shape at that point in time. That was probably done more than 2 decades ago. In those in those lectures, there is a series of lectures, 3 lectures on introduction to data structures 1 and 2 and 3. and there are 3 lectures on recursive definitions. And you will see the complete implementation of all the 3 problems in C language code is given there. I will request you to go and see that so that we don't have to repeat it here. Finally, what we will see is that while this tournament data structure is a data structure we discussed, we will see that there is a very interesting data structure which we shall study, which is called a heap data structure. This heap data structure is a more efficient version of this tournament data structure, which uses only n elements and stores it in an array of size n, and does this whole thing of finding the largest, second largest, and the whole of sorting, the same process that we did using the tournament in a more efficient manner, and that will be discussed in a subsequent class. So, when we started this process, we started algorithms plus data structures equal to programs. We saw that our initial solutions and analysis and refinement and data structures gives final algorithm. We saw 3 examples of problems where we had, in both these, we had 2 kinds of initial recursive definitions. We used recurrence equations to find them and get the optimal splits. Then we saw which is the optimal split of solution refinement, build up the recursion tree, called it a tournament, and then found out that in each of these 3 cases, there are 3 kinds of things that we need to save and remember as we proceed in developing the algorithm. So this is the process. We have got our process now is the initial solution, where we have a recursive definition, then we get the inductive proof, then we get the analysis using recurrence equations, and we have seen 3 cases here. Then we unfold the recursion tree, examine the structures formed and the recomposition properties. We will come to this in more details in later classes. Then the choice of solution. We have seen a case of balancing the split. We will see more cases of other issues which will come up later in more examples that we shall do. Then we saw how to remember past computation for future use, and we saw one example of this tournament data structure. We have seen the space complexity. In our space, the space required in max is only one additional space is one temporary variable. In addition to the memory that we have, we need 2 temporary variables, and we need not store all the original values. We can only read them 1 at a time or 2 at a time and solve the problem. But for max 1 and max 2, we need to store all the elements. We cannot just read them and throw them away. Then we will not get an efficient algorithm. Then we can get at best the 3n by 2 minus 2 algorithm. But if we are to get an n plus log n algorithm, then we will not be able to do it unless we store all the elements till the end of the program. So the space complexity along with time complexity is an important factor, and like the theory of relativity in computer science, we will see that there is a time-space relationship. Finally, how do we get the eventual algorithm? There are other issues like pruning, and in implementation we will see later on, if you are given less memory, for example, we are told you cannot store the original array ever, you can only have 3 variables. Then for max 1, max 2, we have no other option than to use the algorithm that we have used for splitting into 2n minus 2. But if you are given more time, some algorithms will give you only reasonable amount of time and not allow you infinite amount of time to solve. So how will you solve it? So with these 6 steps on the left hand side, We will then come across to solve these core methods which are known as the standard methods of algorithm design: divide and conquer, greedy, dynamic programming, branch and bound, advanced data structures. We will see some important problems: sorting, searching, strings, graphs, combinatorial optimization. And then we will do time and space complexity, lower bounds, and several other aspects. With this, we come to the completion of this lecture. In the next lecture, we will continue our study of recursive formulations and go deeper into some of the issues that we still did not address through a series of new examples. Thank you very much. I would also request you, as I mentioned earlier, not only to look at the videos of this course, but there are a series of NPTEL lectures where we have discussed these recursive definitions, the way we form these data structures, and some of their implementation and the code. It will be good if you have a look at that. If you have any questions, please fill up the Google Sheet for this class and send your doubts, and we will be happy to try and answer them. Thank you.